Okay, let's get started. So, similar to what we did last time, where we defined some impedances, we want to define two other impedances today. Yes, I know we had spoken about the iterative impedance. We're going to look at that again today. So the iterative impedance, or iterative impedance, is the value of impedance which, when we connect it to one of the two ports, produces an impedance of the same value in the other. All right. So in other words, if I connect ZA, if I connect ZA to port B and then measure the impedance at port A, then I will get ZA. And that's my iterative impedance for port A. Yeah. Similarly, if I connected ZB, the iterative impedance at port A, which would be ZB, and then I measure the impedance at port B, then I would get ZB. All right, and that means I would have the iterative impedance. So last time we mentioned this as relating to unsymmetrical networks. And then, of course, if they are symmetrical, we would have the characteristic impedance. However, today we're going to fine tune that a bit. All right. So we go further and we define another impedance known as the image impedance. So the iterative impedance, I put it at the other port, and when I measure the opposite port, I'll get that impedance. For your image impedance is defined as the impedance which, when I connect it to the terminals of the network, equals the impedance presented to it at the opposite terminals. Now I can tell you straight up that that doesn't make much sense, eh? Doesn't sound like much. And then we go further and we say that if the impedances are equal, then it is called the characteristic impedance. So let me try and break down, and this is not my usual style, but yeah, sometimes you have to concede that just mentioning numbers may make the explanation a little easier. Not my typical style, but anyway. So let us say I connect an impedance of 750 ohms at port 2. And then when I go to the port 1 and measure the impedance, I get 400 ohms. Yes? When we talk about image impedance, is that if I then connect, listen carefully, if I then connect 400 ohms at port 1 and measure the impedance at port 2, I'll get 750. Yes? So let me try that again. Talking about image impedance. Yes? I'll use different numbers. Let's use 10 and 20.
Question, sir, are you writing?
If I, you should be writing. If I connect 10 ohms at port 1, or rather, if I connect 10 ohms at port 2, and then go to port 1 and measure the input impedance, and I get 20 ohms, then we say we have image impedance if, when I connect 20 ohms at port 1 and measure the impedance at port 2, I get 10. So I get what I would have had there initially. So in other words, if I connect ZB, sorry about that, if I connect ZB at port B, and then go to port A, and I get an impedance of ZA. So I measure the impedance at port A, and I get ZA. If I then connect ZA at port A, and I go and measure the impedance at port B, I'm gonna get what I had connected at B. And that's how image impedance comes about. Now, this, if we're just stating it, may not be very clear. So let's take an example. Just write down what you have on the screen, and then we take the example. And remember now that if the image impedances are equal, then it's the characteristic impedance. And the only way for the impedances to be equal is if we have a symmetrical network. Yes? So if I have a symmetrical network, then ZB and ZA would be equal. And so if I put ZB here and measure ZA, when I put ZA, I'll get the same value. All right? If I'm dealing with a symmetrical network. So the image impedances, if equal, would be the characteristic impedance. So the image impedance would refer to, generally speaking, an unsymmetrical or asymmetrical network. All right? Okay, so take this question. So we want to determine the image and iterative impedance for the network shown. Now, the same formula that I asked you last week to go and look at for the pi network, we did it for the T network. I asked you to go and prove it for the pi. The same formula that we used in calculating the characteristic is what we're going to use in calculating the image impedance. All right? So for your image impedance, looking into port A, yes, it's given by the product or the square root of the product of the open circuit and short circuit impedances. For our circuit, the open circuit impedance, our open circuit impedance would be 200 in series with 100. And of course, if I short circuit the port, it will be 200 in series with 100 in parallel with 300. All right? Don't think we need to spend a lot of time worrying about that. So our short circuit and open circuit impedances are shown. All right. So it means, therefore, that our image impedance looking into port A is 287.2. If I now move to port B, again, we're using the same formula. Yes. That will be the square root of, again, of the open circuit and short circuit. For the open circuit, looking from B, it will be 3 plus 100. And for the short circuit, the 300 plus 200 in parallel with 100. So we get 367, which gives us OB to be equal to 383 ohms. So the image impedance from B is 383. So let's put this all together, and I apologize for the noise in the background. Hope it's not too distracting. All right, let's put all of this together. So if I were to now connect 383 at port B and calculate the impedance seen at A, I now get 287. All right, so we have 200 in series with 100, which is in parallel with 300 and 383 in series. So the product over sum, and we find that, we get 287. So go ahead for me, connect the 287 at port A and find the impedance looking into port B. Has anyone been able to confirm?
Yes, sir.
Yes, sir. Yes, sir.
So,
Yes.
Yes, sir.
I'll move on then. All right, so for the iterative impedance, we'll have to take this from first principles, because by definition, it's the impedance which when we connected at the other port, we get that value at the input. So if I were to connect ZA, then the impedance seen looking in would be ZA. If I connect ZB, then the impedance seen looking in would be ZB, all right? So similar to what we did when we were deriving the expression for the characteristic impedance, the impedance seen looking into port A would be 200 in series with 100 in parallel with 300 in series with ZA, which is what we have here for resistance equation or impedance equation, which you should all be experts at by now. All right. So simplifying, so we get ZA to be 285.
Excuse me, sir. Could you please go ahead to repeat that before this, please?
Pardon?
Could you go ahead to repeat before you said this, before this slide? Please.
No, I just gave the diagrams with ZA and ZB. So we connected them to the port and got the impedance at the other port. So it was connecting those impedances and calculating the impedance at the other side, which is, as I said, similar to what we did last week. From this, you would have gotten a negative value, but of course, you would ignore that one. So you take the positive value for ZA.
So, and in this case, you say if it was, this means if it was iterative, right?
Yeah, this would be the iterative impedance.
Okay, okay, okay.
And if we now go to port B, all right, which is what I wanted to do. So you're now going to connect ZB at port A, yes, and the impedance looking in would be equal to ZB. So do that calculation for me, please, and find the iterative impedance for the other port. Very clear. All right, so what answer you got?
Sir, I got 385.41.
Okay, thank you, Mr. Marsh.
Yes, sir.
All right, so that's 385.4. So just to confirm, if we connected the 285.4 at port B and calculated ZA, we'll get 285.4. And if I connected the 385.4 at port A and calculated ZB, I get 385.4. All right. So these special names that we will give to impedances, characteristic impedance, iterative impedance, image impedance, all these names, I have introduced you to them now. And so regardless of the area that you'll be focusing on going forward, you'll see these names popping up again, even though, as I said before, you'll see them with names such as surge impedance, etc., etc., etc. Okay? All righty then. So let us take it one step further. Any questions? Or you just allow yourself to do a few more examples, yeah? All right. So earlier, or I shouldn't say earlier, last week, we said that the operation of the circuit, if the operation of the circuit is described using different parameters, that we can describe the complete operation when we connect a load or we put a certain input. All right? Or in other words, when we make adjustments to the external circuit, if we have these parameters, then we'll be able to say what will happen in these external circuits. So if my network can then be looked at as a black box, I don't need to know what is in there. But if I know the parameters, the various parameters that describes its operation, then when I put the load on or I put a supply on, yes, I can say how much power will be taken from the supply, and I can say how much power will be dissipated in the load, or how much energy the load will consume, all right? And these parameters that we're going to be looking at are your admittance, impedance, hybrid, and transmission parameters. Now, in introducing this part of the module, I use a single circuit, one circuit, and I find all these parameters just for you to hopefully appreciate that, you know, it doesn't matter how we define the circuit, yes, we'll always be able to determine its operation or its impact on the operation of the overall system. So let us get started. So we start with what I consider to be the easiest set of parameters to determine. So we start with the admittance parameters. So for the admittance parameters, the input and output currents of any two-port network can be determined from these equations. All right? So we have two equations which we use to define or to determine the input and output currents. Now, students, remember when we just started two-port networks, we gave you some basic principles, yes? And we indicated that the input current, which in this case would be I1, yes, is going in at the upper terminal. Do you remember all of that? And we spoke about the voltage V1 and V2.
Yes, sir.
Beautiful. That's the same thing we're referring to here. And remember, currents are going in at the upper terminals. All of those principles, yes, must be applied when we're doing this. Okay, so having put in that reminder, all right, these two equations are used to define or to determine rather the input and output currents of our two-port network. And the equations are formed by applying the superposition principle to the network. Now, the parameters that I was referring to earlier, we talk about admittance, impedance, hybrid, etc. These parameters are basically the multipliers of our voltages, right? In this case, we're talking about the admittance parameters, yeah? So where do we go from here? I want to be able to determine these parameters, y1, 1, 1, 2, 2, 1, and 2, 2, all right? So let's start with y1, 1. And if I apply superposition principle, and let me ask, how do we make a voltage zero? I mean, we have been doing superposition. How do we make a voltage zero? How do you make a voltage zero?
Short circuit.
We short circuited. Beautiful. All right. And if I had a current, what would I do?
Open circuit.
Open circuit. Beautiful. Beautiful. I see networks one is still strong in you. All right. So we start. So just confirming what you just said. To make these voltages zero, we're going to short circuit the relevant port. So if I want to make V2 zero, I short circuit port 2. If I want to make V1 zero, I short circuit port 1. All right, so for the first equation, I remember we're using superposition principle. I sound like the student today, but anyway. I1 is going to be equal to Y11 V1 under the condition that V2 is equal to 0. Right? So if I make V2 0, this is all I have left in the equation, which means that I1 would be equal to, or Y11 would be equal to I1 over V1. Right? And if I were to now go through and look at all the parameters, I can determine them in a similar fashion. Don't get too scared. It's actually very easy. You soon get to the easy part. All right. So for the other parameters, if we wanted y12, yes, then y12 would be equal to I1 over V2 with V1, V1 is 0. If I wanted y21, then it would be I2 over V1 when V2 is 0. And then, of course, Y22 will be equal to I2 over V2 when V1 is equal to 0. Now, what you would have figured out by now is that now that you have graduated to networks 2, one of the topics you are going to, or one of the mathematical methods you are going to be running into a lot is matrices. Yes. So we can form a matrix from the two equations that we had. Yes. So I1 and I2 will be equal to these admittance values times the voltage values. Nothing fancy about that. So in other words, what we have is I is equal to V, or Y, sorry, times V. So let us make our first attempt at making this thing simple. All right, so this is my first attempt at making it very simple. I hope I succeed. All right. Now, if you know, just like when we're doing mesh analysis and nodal analysis, and we introduced the matrices, the position in the matrix meant something, right? So we're going to apply the same principle here. The position of the matrix element indicates which ports are being compared. So Y21, first of all, it's Y. So if it is Y, you know it's an admittance, no?
Yes,
And
sir.
2, 1 tells you that you're dividing port 2 by port 1. So Y21 means that you're dividing 2 over 1. The next question, however, is what 2 and what 1 am I dividing? Of course, we know that admittance, so it tells us that it's a Y. We know admittance is current over voltage. So therefore, Y21 would be equal to I2 over V1. I think I am successful in making the first part simple.
Yes, sir.
Note, however, that in writing the individual parameters, I write lowercase y. However, when we write the matrix, that's when we use capital Y. So the individual elements are denoted by lowercase y, but the complete matrix would be equal to capital Y, or be represented by capital Y. All right. Point number two. The nomenclature used to describe the parameter is dependent on what is done to the port when we derive its value. So when we are finding Y21, port 2 is short-circuited. So in other words, these are short-circuit parameters because we had to short-circuit a port in order to find the respective values. All right. And then thirdly, the third big point to note.
Wait, sir, can go back, please.
All right.
Yes, sir.
Okay. And the third thing we need to note is that Y21, yes, it involves both the input and the output. So it has an input current and an output voltage. Yes. It is therefore referred to as a transfer parameter. So transfer because we are dealing with input and output. So we're mixing in and output, so it's transfer. Okay? So the complete name for Y21, remember we first said that you have to short circuit a port? So the full name is the short circuit transfer, and of course, it is an admittance. So it is a short circuit transfer admittance. Nice and easy. Everybody can see that? Nobody have a problem with that? Yes, no, maybe? All right, I love the silence. So, Mr. Black. Mr. Black? Mr. Black is on silent night. Sawyers?
Yes, sir.
Okay, Mr. Sawyers. Give me the full name, therefore, for Y12.
Hello.
So, Sawyers, what you got?
Yes, sir.
Yeah, I want the name. Give me the name for Y12.
I'm not sure, sir.
All right. Mr. Black, give it
Yes, sir.
that try.
Say you hear me?
Yeah, I'm hearing you now.
Sorry, it's the name for which one? Y11?
1, 2.
Or 1, 2?
All right. So, Ms. Hansen, you're next in line. Hansen,
Hello.
Y12, name, full name.
Full name, I would say open circuit transfer admittance.
Did you open circuit anything?
No, sir.
What did you do?
Short circuited.
How you call it open circuit one? Huh?
So I don't know. I didn't have a reason.
You just want to give me one wrong answer.
So
Mr.
it'll be
Brown?
short. Oh, okay.
Mr. Brad? Chad?
Yes, sir, I'm here.
Yeah, man. Give me a name for Y12.
A name for it?
Yeah, man. I just asked if anybody had a problem. No, if everybody was silent. No, I'm asking you for the names and nobody can give me.
No, but I'd say the same thing, the short circuit transfer admittance.
Thank you very much, Mr. Brand. Since you got that one, it rolled off your tongue. Let's try Y11. What do you think that would be?
Why 1-1?
Mm-hmm.
I think in that case it would be the open circuit transfer admittance.
Did you open circuit anything?
At that,
In
I mean,
order,
like, dealing with
all
both.
these, in order to find all these parameters, didn't you
Yes,
make
sir.
a voltage zero?
Oh, yeah, no. So everything would be the short circuit transfer.
Thank you very much. So Y11,
Yeah, and Y22 is just the
No,
same.
no man, you're not finished with Y11.
Y11 is the name for it is short circuit transfer admittance.
Why you say transfer?
Oh, there is no yeah, it's the same port, so there's no transfer between input and output of the different ports, is it?
Well, transfer if you're dealing with the two ports, but you're dealing with only one now. So what you call it?
Forward.
The short
Forward.
circuit forward admittance.
Oh,
Or
man.
short circuit admittance, I should say.
Yeah.
Mr. Hodges, thanks, Brian. Let me hear Mr. Hodges. Mr. Hodges, what do you think?
The short circuit forward admittance. Sorry.
What you gonna forward? What you reach us up? Eh? What you reach us up, Mr. Hodges? All right, why did I say that we had transfer admittances? Why did we call them transfer? I was just welcoming you to flow. You know, we really need to fix this nonsense now. This is the start of the school year.
Sir,
I got messed up yesterday and I'm getting it today. Anyway, I apologize for that.
Yes, sir.
All right, so let's come back now. With why did I call it transfer?
It was
Both
between-
input and output connected.
Input and output.
All right, so it's using both input and output, right? So work with me now. What is Y11?
sir, would it be
Uh,
Input admittance.
Input admittance.
admittance.
Exactly.
Short circuit input admittance.
Short circuit input admittance. And therefore Y22?
The short circuit
Output admittance.
Short circuit output admittance.
That's all like school challenge now. All right. So let's jump into a little exercise. Take that circuit for me, please. All right, now, going back to our equations, we had I1 is equal to Y11 V1 plus Y12 V2. And of course, I2 is equal to Y21 V1 and Y22 V2. I don't recall if I had mentioned the fact that in terms of the matrix, that the subscript tells the position in the matrix. All right, so 1, 1 would be position 1, 1. Yes, 1, 2, row 1, column 2, 2, 1, row 2, column 1, etc. All right. So not only are you able to tell what is being divided by what, but you're also able to determine where in the matrix the particular parameter falls. All right, so going back to our question. So we have our circuit, simple pi network, and we want to find the admittance parameters of the circuit or of the network. So the first thing we want to do, let us short circuit port 2. All right, so I've put a short circuit on port 2. Now, if that port is short circuited, what would be the impedance looking into the into this port?
5 in parallel with 10 plus 20. 10 in
Okay.
20. 5 ohm in parallel with the 10 ohm in period 10 ohm.
Anybody disagree with that?
Yeah.
Yes, sir.
Now, what you say, Mr. Marsh?
So I would say the 5 ohms in parallel with the 10 ohm resistor.
So it's just 5 in parallel with 10.
Yes, sir.
Yes, sir. Agree with you.
Absolutely. We have a short circuit, so it means that that would have been bypassed. All right. So V1 over I1, which of course would be the impedance looking in. Yes, V1 over I1 would be equal to 5 in parallel with 10, which is 10 over 3. So I1 over V1, so we just find the reciprocal. We just flip it in order to find Y11. Would be 3 over 10 or 0.3 Siemens. Everybody comfortable with that?
Yes, sir. Yes, sir.
All right. Now,
Understood.
since I already have port 2 short circuited, I'm just gonna go to the second equation and I'm gonna find Y21. All right, since we already have the port short circuited. And remember now, Y21, let's see if you're following. Y21, what would that be equal to?
I2 over V1.
I2 over V1. Beautiful. Now from this circuit, where will I2 be flowing?
Into the 10, sir.
Into the 10 ohm, because of course, with the short circuit, these two are in parallel, which means that what's the voltage across both of them? What's the voltage across the 5 and the 10?
V1.
Huh?
V1.
V1. V1. Beautiful. So with respect to the 10 ohm, with respect to the 10 ohm, what's the relationship between V1 and I2? Because we agree, we have just established that V1 will be across the 10 ohm. Yes? So what's the relationship between V1, the 10 ohm, and I2?
I2 would be equal to V1 over 10.
I2 would be equal to?
V1 over 10.
All right. Correctish, Mr. Black. Clean up that one for me. Anybody? He's wrong, but not totally wrong. So come again, what's the relationship between V1, I2, and the 10 ohm resistor?
V1 is equal to 10 I2.
V1 is equal to?
10 I2.
But that's exactly what he said. And I'm saying he's wrong, but not totally wrong.
minus 10.
Thank you, Mr. Gale. So V1 is equal to minus 10 I2 because remember the convention I started with? And you remember the one I gave you last week? That I'm going to start with some very simple things, but they are going to be fundamentally important, of fundamental importance to your understanding of this topic. All right? Don't take anything I say to you lightly. So the current is coming in this direction. However, we know that for V1, the potential at this point is high with respect to that. So it means that the current as a result of V1 will be going that way. So based on that, V1 is equal to minus 10 I2. And so from this, we cross multiply, we bring that over, bring this over. Yep. And so Y21 is equal to minus 0.1 Siemens. We clear on that?
Yes, sir. Yes, sir.
Beautiful. So what I want you to do for me then, since you know, all right, let me not. Yeah, yes, why not?
Sure, right. Sir.
So since you understand it, I want you to now find Y12 and Y22. All you're doing, you're now going to short circuit. You're now going to short circuit port 1 and then find the relationships looking here. So go ahead for me. Find Y12 and Y22. Ms. Richards, you have an answer for me? Dana Richards?
Hello?
Y22.
So I was going to do I2 over V2.
Okay, what did you get?
Yeah, I don't finish. I was just looking at it.
You was looking at it?
Yeah,
okay.
I was going.
All right, has anybody found Y22 or Y12?
Y22, sir, is 0.15 Siemens.
Go again?
0.15 Siemens, sir, for Y22.
Y22 0.15. All right. Mr. Brian, you have your hand up. Thank you, Mr. Pero.
No,
Mr.
sir,
Brian?
it's still up from last time. Sorry.
Okay. Humphrey? That's why Y12.
Y12 is I1 over V2. And the answer for that is going to be
Yeah, Mr. Humphrey, are waiting. So we have Y22, Y12, Come on, students, that's the easy of the two, you know. It's the same reasoning for Y21.
Negative 0.1.
Okay, Mr. Hodges. So 2, I2 over V2, right? That's the 20 and the 10 in parallel. And Y12 would be equal to minus 1 over 10. So I can now write my admittance matrix. So it will be 0.3 minus 0.1 minus 0.1, 0.15. So remember how we started. We said that if you had the parameters, you could use them to analyze the network when we connect something at the output and at the input. Okay? That's what we said earlier. So let us use that, or use these parameters and see, well, let us see how we can use these parameters. Yep, getting ahead of myself. All right, so take this question for me, please. I resume the recording. All right, students. Now, circuit before you, nothing fancy, right? If I had asked you to calculate the power dissipated in this 4 ohm resistor and gave you this circuit, you'd have no problem. You could easily write your resistance equation and do your thing. Not a problem. However, inside this network, you have the circuit that we just analyzed. We just found the admittance parameters. All right? And I'm asking you to use the admittance parameters in determining the power dissipated in the resistor. All right? So let's see how we go about doing that. So I'm going to write my equation again. So the equations, I1 is equal to Y11 V1 plus Y12 V2, and I2 is equal to Y21 V1 plus Y22 V2. All right, so we always start with our equations. Right? That's my equation 1, that's my equation 2. Now, we have the values of Y11, 12, 21, and 22. We only have 2 equations, but how many unknowns do we have here? How many unknowns do we have?
4, sir.
4. And we need a maximum of? The maximum number maximum of 2.
2
All
unknowns.
right. Beautiful. So let's start with the output side of the circuit. We have V2, we have I2. Can we write a relationship, or can we identify a relationship between I2 and V2? Anybody? What's the relationship between I2 and V2 based on this circuit?
V2 would equal to I2 for I2.
All right, so Swebe is saying that V2 is equal to 4 I2. Not a bad attempt, Mr. Swebe. Anybody want to clean that one up?
Minus I2, 4I2.
Why minus, Mr. Gia?
Sir, because of the rule we're currently flow from positive to negative, but I2 is going in the opposite direction.
Thank you very much. Ladies and gentlemen, the fundamental principle, and I just said it when we were looking at deriving the parameters. I said up here, so higher potential relative to down here, so. So therefore, for V2, the current would go in that direction. However, I2 is going in this direction, so this must be minus. So that's the output side. So we have removed one of the variables, because we can now substitute for V2 in terms of I2. So we'll be left with 3 unknowns. So I need to now get rid of either V1 or I1. So we go to the input side of the circuit. So on the input side, I1 is the current going into the network that we already know, right? V1 is the voltage at this point. So I want you now to look at the circuit and tell me what the relationship would be between this source, I1, V1. What would be the relationship? Come on, talk to me.
V1 is equal to 10 I1 plus 15.
Go again. You said V1 is equal to?
10 I1 plus 15.
No, that's not correct. But there are several other reasons why it couldn't be correct. One of them is that it is dimensionally impossible. You remember when you did dimensional analysis in physics? So you cannot have V1 being equal to anything plus the 15 because V is a current, is a voltage, and the 15 is a current. So that expression could never be correct.
Times the 10.
Go again.
Go on, 15 times the 10, 15 amps times the 10 ohms equal V1.
But is the 15 ampere going through the 10?
No, sir.
No. Come on, put on the networks one hat.
Sir, would it be?
I have an equation, but I don't have.
Hold on, Ms. Campbell. Hold on, Ms. Campbell. Let me hear Mr. Stewart.
Sir, would I1 be equal to V1 over 10 ohms plus the 15 amperes? I was saying I1 is equal to V1 over 10 ohms plus 15 amperes.
Let me hear Ms. Campbell. I'll come back to you, Mr. Stewart. Ms. Campbell, what were you saying? Give me your equation.
Sir, I was saying that I1 plus 10 V1 is equal to 15 amperes.
But for the same...
Somebody have to take it from there.
No, but for the same reasons that I said, Mr. Peru was incorrect. Yours would be incorrect. But Mr. Stewart is the one who is closest, but he's just being lazy. So maybe give him one more chance to correct it.
Yes, sir. Negative I1 is equal to...
But Mr. Stewart, I1 can only go in one direction. No, give me no negative.
Okay, sir. So I1 is equal to negative 15 amperes minus...
Why are you turning around the people in current source, huh? Oh, you're powerful, so leave the people in circuit alone. All right, so you have messed it up. I was hoping that you would give me the right answer on the second bite. Anybody else want to try?
Sir, I1 is equal to V1 over 10 plus 15.
But that's what Stewart said, and I told him to correct it.
50 minus V1, 10 ohm.
Go again, Mr. Facey.
It was 15 amps minus V1 over 10.
Equal what?
I1.
Beautiful. Thank you very much, Mr. Facey. People, all you're doing is applying Kirchhoff's current law. That's your node. The current flowing into the node is what? 15. The current leaving the node is I1 and 10 over 50, V1 over 10. No, sir?
Yes, sir.
Yes.
All right. So I1 is equal to 15 minus V1 over 10. So we now have the expression. So I1 is equal to 15 minus V1 over 10. V2 is equal to 4I2. So I make the substitutions. This is I1. Remember, you know, I start with this set of equations. Yes? And I'm now making the substitution for I1 and for V2. So wherever I have V2, I put in 4 minus 4I2. So we put those in and we solve and we get V1 to be equal to 40 volts and I2 to be minus 2.5. And then when we substitute in our original equations, we get V2 to be 10 and I1 to be 11 amperes. Of course, I don't need to work out the power. You can figure that out yourself. Any questions?
Sorry, why you say it couldn't work before again?
What couldn't work?
The way that we were expressing it before.
Okay, did wrong.
Repeat, please.
It was just wrong.
Oh, get it now, sir.
There's no other way about it. It was just incorrect. So you're just applying Kirchhoff's current law. Remember the principles, Ms. Campbell. Very important. Again, up here is at a higher potential than down here. So therefore, for this 10 ohm resistor, the current must be going down. There's no two way about it. So V1, the higher potential, is at the top. So those things we dealt with last week, you can't forget them. They are fundamental. They are the bedrock of what you'll be doing.
Okay, sir, I see where I went wrong. Thank you.
You're welcome, ma'am. All right, so any other questions?
I bring it back. Can bring up the page a little, sir.
Huh?
Yeah, the page a little.
This one?
Or the other page.
And that's where I was.
Sir,
Yes.
sir, in determining the admittances, you said, sir, well, following how you would get the admittance for the
Is that Thompson? All right, type your question in the chat. Okay, so while I wait that question, we want to now look at the next set of parameters, which are the impedance parameters. And for the impedance parameters, remember the admittance parameters gave us a relationship for the current with respect to the voltage. Impedance parameters just turn that around. What we're going to have are the voltages with respect to the current. All right? So we'll have V1 and V2 with respect to I1 and I2. Again, we apply superposition. And what we asked earlier was how do we make a voltage zero? You rightly said short circuit, and we asked about the current. You said open circuit, and we're just going to apply that here. So the impedance parameters are what we call open circuit parameters. So let us see if you were actually listening to me or making sense of what I was saying earlier. And if there are persons in this class who are simply depending on the recordings, I am strongly urging you not to do so. And that's the last time I'm going to say it. If you hear it from me again, you get 10% free for going at the final exam. All right. So.
Remember that, sir.
Yes, man.
Sir, can I repeat, please?
Huh?
Can I repeat, please, sir?
Yeah, man, I'm repeating. V1 equals Z11 I1 plus Z12 I2.
I remember that.
Is that clear now?
Yes, sir.
So, based on what we have here, what would Z11 be equal to?
Open circuit input impedance.
Yeah, but what is it equal to? That's a name, which is correct. That's a name we would give to it. Or would we find it?
You would find it by making I2 equals 0. And you'd basically transpose. So it would be V1 upon I1.
All right, so it's V1 over I1 with I2 being equal to 0. Thank you very much, Mr. Hodges. I think the approach or the engagement we have over the summer was worth it. I am trying to adopt that method, but anyway, we'll see. So Z11 is V1 over I1. What? Let's see now. Let's see if I can find a name. I need a name. So Jens, why you have to? Why are you here twice? So Richards, Joel.
Yes, sir.
Z21.
That would probably be the. Oh, you want the name of it or the value?
Oh, you find it.
You would open circuits I2, and that would give you a V2 over I1.
Thank you. All right, I think you all have it. So I can move on. So we open circuit the ports, yes? And so we have here Z11 is equal to V1 over I1 with I2 being equal to 0. Yes? Z21, sorry, 2 over 1 with I2 equals 0. And just to note, the 2-1 and the 1-1, we do it at the same time because the same port would have been impacted in order to find that. All right? 1-2 is V1 over I2 with I1 equals 0, and 2-2 equals V2 over I2 with I1 being equal to 0. All right? And there are no masters with the names. So Z11, as Mr. just correctly said, would be your open circuit input impedance. Z21 would be your open circuit transfer impedance. Z12, again, open circuit transfer impedance. And Z22 would be your open circuit output impedance. All right. So you can fill in those names.
Sir, I was asking how to find the transfer admittance.
Pardon me?
I was asking how to find the short circuit transfer admittance, but I realized that based on the description that you gave before the notes, the short circuit, the port that the first element in the subtext, the subscript, and then analyze the circuit to determine the impedance and then invert that to find the admittance.
All right. So you want the confession now?
Oh, yes, sir.
The confession is I don't understand a word you just said, but I'm going to agree and say, yeah, man. Oh, that's all. I really don't understand it. But I know what you say. I know you're trying, but I don't want you to complicate it by trying to, remember all of those things, Mr. Thompson. Let us start by looking at the equations. Get into the habit, and I am emphasizing this because when we start to look at the other parameters, which are a lot more complex than what we are now looking at, it's the equation that is going to tell you what you do in terms of the respective ports. So please, don't try to say, well, this is the one. Start with the equation and apply superposition. All right?
Yes.
Okay, so here's our matrix equation. Yes. And so I'm going to once again go back to our trusty network. Remember I told you I'm going to use the same network, and then we are going to find the various parameters. I use them in terms of circuit analysis. Huh? Okay. So I'm finding Z11. So Z11 is equal to V1 over I1 with I2 being equal to 0. And if I2 is 0, it means that we have an open circuit at port 2. So in other words, it's just as is, and we're looking at the impedance here. All right? So if I open circuit the port, then it is 5 in parallel with 10, which is in series with 20. I know I have put the decimal here, but just keep it as a fraction. Just keep it as the 150 over 35. Still with port 2 open, I'm going to find Z21, which is V2 over I1. Now, let's go through the process. All right, so here's our network. And I want the relationship between V2 and I1. All right. What you're going to do, students, is simply to track I1 and see what component of I1 will pass through the 20 ohm, because the V2 is across the 20 ohm. So don't tell me what the values are. I want to know what approach you're going to take in determining the component of I1 that passes through the 20 ohm. Anybody?
Current divider.
Current divider. All right. So you're dividing I1 between, Campbell?
Yes, sir.
What are you dividing I1 between?
Between the branch with the 10 ohm and the branch with the 5 ohm resistor.
So you're dividing it between 5 and 10?
Yes, sir.
Think about it carefully. Why 5 and 10?
Yes. A V2 is short, sir. Oh,
No, we
because
want,
the 20 volt, the 20 ohms, sir.
no, we
Sir,
have a,
repeat your
we have a,
question, please.
we have an open circuit here, you know.
Right,
It's open.
right.
So the current that goes in through the 10 ohm, where will it go?
It would also go through the 20 ohm.
Exactly. So what are you dividing the current between?
Between 5 and 30.
Absolutely. All right.
Yes,
And that
sir.
will give us the current through the 20 ohm. Agreed?
Yes, sir.
And if I have the current through the 20 ohm, I can find the voltage across the 20 ohm.
Yes, sir.
And if I know the voltage across the 20 ohm, what we call that voltage?
You call it the
We call it
open circuit.
V2.
Oh.
V2, just V2.
Okay.
All right.
Yes, sir.
So current divider between the 5 and 30, we get 5 I1 over 35. And that will be the current through the 20 ohm. Of course, you recognize that I'm skipping a lot of steps because, you know, that's why we have prerequisite, eh? So we have the voltage drop across the 20 ohm, 20 times that current. So we get 100 over 35. What we want is Z21, which is V2 over I1. So we simplify and we get that. So this is Z21. Everybody comfortable with that?
Yes, sir.
All right. So based on what we have done here, let's go back to our circuit. I'm removing the ink. I now want Z22. With Z22, it means that port 1 or I1 is equal to 0. So we open circuit port 1. So I'm now looking inside here. And Z22 would be V over I2. So what's the impedance seeing looking into that port?
Twenty
in parallel with the summation of. Go ahead, sir.
20 in parallel with?
15.
With 15. All right. Good. And for Z12, yes, we do the same current division. So the current I2 would divide between the 20 and 15. All right. And then, of course, the V1 would be 5 times that current. So we can now go to All right. So we end up with this as our matrix equation. V1, V2, 1 over 35, 150, 100. All right, so as I said, even though I had put them in decimals, I would prefer if you just kept them as fractions. Makes life easier, as you will see soon. All right. Can I move on? All right, that means yes.
All right, sir.
So I'll come back to the same question. All right. Remember our trusty question. So what I want to remember now, we're going from the equation V1 is equal to Z11 I1 plus Z12 I2, and V2 is equal to Z21 I1 plus Z22 I2. All right, so that's where we're starting. We have already established the relationship between V1 I1 and the input, and we have already established the relationship between V2 and I2. Okay, you now have the values for the impedance parameters. So you have the Z matrix, 1 over 35, 150, 100, 100, 300, yeah? So you already have that. So go ahead for me quickly. All right. I have 18 minutes and I want to make one last statement before we wrap up. So go ahead for me and calculate your currents and voltages. Please don't forget to use the 1 over 35. All right, so do that for me. Give you 5.
Excuse me, sir.
Go ahead.
Sir, I was right. I was jotting down something while you were talking. Could you repeat what you asked us to find, please?
The same thing we found for at the beginning. Let's find the values of the currents and voltages.
Oh, yes.
But there was a solution. Yes, man.
So isn't it just the same solution as what we got before?
Yeah, you get the same values.
Yeah, that's what I do.
Remember, that's the principle that we are trying to get across. The principle is that regardless of the parameters, once you have the parameters, whether they are the admittance parameters or, based on what we have been introduced to this afternoon. So whether it's impedance or admittance, the operation of the circuit will remain the same. All right, so I am able to define this. So when we go a little further, you will find that maybe we are able to define let's say this and then we define this, okay, and connect them. So this is how we go about building systems. So I'm able to define this part of the system, I'm able to define this part of the system, and then I connect the systems together. All right, but that's what we're after with this particular topic. All right, so since Mr. Stewart let it out, and we all know that you should get the same, the last point I want to make to you this afternoon, and by the way, given what we have gone through, what I'm going to ask you to do is just to spend the rest of today. So I'm not going to have the 1 hour session after this. Please go over the notes, over what we have done today. Formulate your questions. You can put them in a discussion forum, and I will go there and we will provide responses. Okay? And that will also obtain for tomorrow afternoon. I don't want to, the next set of parameters that we are going into would be the hybrid parameters. And I would prefer to do that when you are fresh, because it does take some thinking. So in closing, we just want to make one point. Z11 is not equal to the reciprocal of Y11. Neither Z22 being the reciprocal of Y22. Here we know impedance is equal to the reciprocal of admittance, but it's not for the individual items. What is true, however, is that Z, meaning the set of parameters, is equal to the reciprocal of the set of admittance parameters. All right? So if you were to find the inverse of the Z matrix, you will get the Y matrix. And that is what I'm going to leave you with for today. So please, we have done quite a bit this afternoon. It may not feel like that. It may not feel that way, but we actually have. So next time we meet, I will be looking at the hybrid and the transmission parameters. And then after that, we look at how we interconnect networks and how we derive the overall operation of interconnected networks. All right, so that's it from me for today.
All right, take care, sir.
All right.
So what is our class tomorrow? Question, sir.
Yes, Mr. Pero.
As I was here as the class started, I came a little bit. The record, you can post it there as a leave.
Well, I'll post it. I don't know what will be the impact of the break in transmission, but let us hope everything is there.
Speaking of that, I'd noticed that when I was looking for the video, because when you went through the first time you went through 2 ports, I was in the first half of the club, but then my internet went, so I wasn't able to attend the second half of the tutorial where you went through the 2-port networks. And I noticed that when I tried searching on your YouTube channel, sir, it wasn't there. The recording of
you're very correct. It was not there because I did not post it.
Yes.
It was just an oversight. It's not that I intended not to post it. I just didn't.
Okay.
I just had quite a few things treating with that evening.
Okay, fair enough, sir. No problem.
All right.
Sir?
Or can I start to come to your Wednesday tutorial instead of splitting it?
Fine with me.
All right, sir.
Sir.
The room can hold.
Okay. See you next Wednesday then, sir.
Yes, Mr. Cole.
Yeah, sometime I won't be able to make this 1 o'clock to 3 o'clock class. I don't know, work JPS and some work. I'm a lineman, so sometimes we have emergency work. So I'm asking if like when we have, if you have in-class exercise, if I can get exemption and maybe submit it the same day at a later time.
Mr. Colon, we appreciate your service. We appreciate your service to the nation, but sorry, that no work here, so. All right. Catch up with the recording. I can't recall giving you an assignment and asking you to submit it, but at least for networks to asking you to submit it the same evening. So you would have had access to the recording to know what was due or what is due. All right?
Sir, and sir,
Okay, all right.
remember to open the link, sir, the upload link.
I can open it right away. I just didn't do it. Because you had until tomorrow evening, right?
Yes, sir.
Quick question, sir.
Yeah, man.
As it pertains to the assignment, sir, if another approach was used for
You get the same
wrong.
answer.
The angles are different, so it's wrong then, sir.
I already didn't put any angles in mind.
Then it was wrong.
All right. Sure. Sir?
Yes.
Sir, hear me?
Yeah, man. Yeah, man.
Yes, sir. You posted the solution to the questions that we got for the assignment. Are we now supposed to just grade ourselves based on?
Didn't I send a message with it?
It's send a message, sir, but
it wasn't clear.
Well, a few people are asking around, and I just want to be clear as to what.
Yeah, but you read the message?
Yes, sir.
Wait, sir.
It said we're supposed to. I think it said so I guess I'd have to read it again. So
what was your first interpretation?
So basically put the grade that we would get based on that solution on it and then re-upload that.
So in other words, mark it and upload it.
Okay.
Okay, man. Where's Miss Brown? Is she still here? Imani Brown. Or she leave the room already. I'm gonna mark the register again today. Oh, I'm getting.
I'm here. One question, sir.
Getting sloppy. Miss Brown left the room already. Okay, Mr. Thompson.
Oh, sir. In question 2, I believe you use mesh analysis to analyze the circuit, and I use nodal analysis. So I was just wondering how I would compare the.
You get the same answer?
Yes, sir.
What the problem?
Oh, because you already have a mark.
Mr. Thompson. You get the same answer?
Yes, sir.
It was for you to find Thevenin equivalent, right?
Yes, sir.
You got the Thevenin voltage?
Yes, sir.
Then what the problem?
There is no problem, sir.
Yeah. So let us not create one.
Sir,
Yes, Mr. Brad.
You had mentioned something regarding a discussion forum. Could you just once more expand on that? Just to clarify.
It's in Schoology. Once you raise a discussion, then everybody will see it.
Oh, okay.
You just start a discussion, and the messages will be shared with everyone, and everyone can chip in.
All right, sir, no problem.
All right. All right, then. Have a good one.
You too, sir.
Mm.